Hi everyone. Today we have the pleasure to have Christophe Gissinger from ENS, who will be giving a quite a different talk from what we are used to, which is about accretion disks, but in laboratories. Christophe, the floor is yours.
All right, thank you very much. Thanks, Raphael, for the invitation. So the focus of this talk will be a bit different, I guess. What can we learn about accretion disk turbulence using laboratory experiments? And as you will realize soon, I'm not an astrophysicist, and I will mostly discuss very simple results obtained from obtaining scaling laws and maybe a little bit of bifurcation theory to say a few things about this topic. So here are the list of the people I worked with on the experimental side here, and for the numerics I will describe at the end of my talk here. So I'm also will be discussing a little bit about magneto-hydrodynamics. So I'm assuming that most of you know what it is about, but let me just in one slide summarize a little bit what it is. So MHD is the study of electrically conducting fluids. So it can of course describe, for example, the plasma in accretion disk or in any ionized gas in astrophysics, like in stellar interiors. It can also be describing the liquid metals in planetary interiors. You will see that in laboratory experiments, it's a good choice in general to use liquid metals and any electrolytes, like salty oceans, for example. Now, we first need to describe the flow motions when we're doing MHD. So, of course, you need to solve the Navier-Stokes equation. The main difference with classical hydrodynamics is the Lorentz force here, where J is the current, B is the magnetic field. And this is simply describing how a magnetic force can drive or modify, sometimes inhibits the flow motions. And most of the time, you also want to discuss the dynamics of the magnetic field. And in this case, you need to couple this Navier-Stokes equation with the induction equation, which is here. And it's obtained by combining the Ohm's law and the Maxwell equations. And roughly speaking, you could say that it tells you that the time variation, the time evolution of the magnetic field, is due to a competition between two terms. The first one here, which is the induction, it involves the velocity, and it basically describes how flow motions can induce some magnetic fields. And it's counteracted by the Laplacian here, which describes the magnetic diffusion, where eta is the magnetic diffusivity. Now, obviously, when you look at this equation, a typical parameter, which is important in MHD, it's going to be the ratio between these two terms, which is called the magnetic Reynolds number. And it looks a little bit like a Reynolds number, except that instead of the viscosity, we are using the magnetic diffusivity. Now, it's very clear that B equals 0 is always a solution of this problem, okay? And in general, when the magnetic Reynolds number is small, B equals 0 will remain a solution of this problem, so you don't have a Lorentz force and you're just doing hydrodynamics. So for example, so I don't know if you see my camera, I bring some glass of liquid metal here. I don't know if you see it. So it's basically, we have some liquid gallium here, okay? And I can, stir this liquid, all right? And I'm inducing some flow. But of course, the magnetic Reynolds number in this example is very small. It may be 10 to the minus 6 or 7. So while I'm doing that, clearly B equals 0 remains a solution of this problem. And so I'm just doing classical hydrodynamics, but with a very expensive liquid. All right. But if I was able to rotate that very, very fast, maybe to increase the size of the system such that the magnetic Reynolds number become large enough, then in this case, we know that the B equals 0 solution becomes unstable. This is a dynamo instability. And so the flow motion here will generate a large-scale self-generated magnetic field. That's the dynamo magnetic field. And in this case, of course, the problem becomes complicated because then you have a magnetic field. It will react back on the flow motions, and you have a nonlinear complicated problem. Okay, so that's basically what we have here for our MSD system. So my talk won't discuss too much about dynamo except at the end, but it's good to have that in mind. Okay, so that's a very short, reminder of what MHD is. And now I will discuss more about accretion disk in the lab. So as a physicist, there is, I think, at least 3 properties that you want to address or to discuss when you're doing a laboratory experiment. The first obvious one is accretion rates. Okay, we know that accretion disk has huge accretion rates, and we know that it means that somehow there is a powerful outward transport of angular momentum in this disk. The second point is that the rotation profile in the disk. We know that there is a force balance between the centrifugal force and the gravitation, which gives these very particular rotation rates, whereas the azimuthal velocity is going like 1/square root of the radius. And the last point, of course, is the fact that some disk or some regions of some disk are ionized enough, so they can be an electrically conducting. They can involve an electrically conducting fluid, and so magnetic field can become important in this disk. Okay, so there is a lot of different important aspects of accretion disk. I know that, but that's like first order interesting things about accretion disk. And already with these 3 properties, we all know that there is some problem. We know, for instance, that we can't invoke, of course, the molecular viscosity to explain the accretion, because the typical time scale with viscosity is way longer than the age of the universe, and you can't explain accretion rates like that. So for a long time now, people have been invoking turbulence, because we know that if the flow is turbulent, it will enhance the viscosity, it will produce some eddy viscosity, and it could explain the accretion rates. But that's not so simple, because Keplerian rotation is supposed to be linearly stable. Okay, you don't have a centrifugal instability. And so there is no obvious route to generate this turbulence we need to explain the accretion. So of course, there is a lot of different mechanisms to explain the origin of fluctuation of angular momentum transport. In some cases, it's even not related to turbulence. So I won't review all of these different scenarios like stratification or cosmic rays or inertial wave instabilities and these kind of things. I will mostly focus, it's not the focus of my talk, but I want to mention one of the most popular one, which is related to the magnetic field, to the last properties of accretion disk I was mentioning, and which is the magnetorotational instability. So again, I won't enter into too much details, but let me just remind, I'm assuming that a lot of people know what it is, but we know that if we perform a linear stability analysis of these equations, if there is a magnetic field, we can make a centrifugally stable flow unstable through the magnetic field. Okay, it's a very interesting instability. It was proposed by Balbus and Ole in the 90s, and it only requires a small number of conditions. We need a magnetic field, we need some differential rotation, and we need the magnetic Reynolds number to be large enough. And in most of ionized disks, these 3 conditions are easily met. And in this case, you can get an instability in your system. So again, I won't give a full description of the mechanism. I put this sketch here just to give for those of you who don't know the MRI, just to give you an idea of what's going on. Roughly speaking, you could say that, so it's like a top view of a disk, okay? And you might say that when there is a magnetic field, there is some magnetic tension connecting the fluid element together, which is acting a little bit like a spring force. And we know that if there is this spring force, if there is a magnetic field, then 2 fluid particles can exchange angular momentum as they rotate on different orbits, and that this can make the flow unstable. Okay, so it's a very powerful linear instability. And interestingly enough, we know that in the nonlinear stage, it can easily give rise to some turbulent flow, so to well-developed turbulent flow. So it's a very good candidate for explaining accretion in accretion disk. So it can be summarized on this very simple sketch. You start with a large-scale magnetic field, and the MRI will generate small-scale perturbations and some turbulence. Okay. But of course, it's only half of the story, because then immediately you're wondering where the large-scale magnetic field is coming from to generate the MRI. And that's how some people arrive to this very simple nonlinear MRI dynamo sketch. Just like the example with my glass of liquid gallium, we know that turbulence, vigorous motion in a conducting fluid, is extremely efficient to self-generate a dynamomagnetic field. And so the idea is that once you have this turbulence, it's very efficient to generate back the large-scale magnetic field you start with. And so you have a nonlinear amplification loop where both turbulence and magnetic field are generated in the disk. All right, so that's the basic idea. Now, going back to my talk, the first part will be almost independent of that. In the first part of my talk, I don't care too much if this is exactly this cycle which is occurring in an accretion disk or some other instability, even perhaps non-magnetic instability giving rise to turbulence. The first part of my talk is to understand if we have turbulence. Is it enough? Does it have the good properties to produce the transport of angular momentum we need to explain the accretion rates which are observed in astrophysical disk? And for that, I will use experiments. And if I have some time at the end, I will address the second part of the talk, or maybe the last 15 minutes of the talk, in which we will try to address this nonlinear scenario. And in this case, I will use a little bit of DNS. Okay, so let me start with the first part of the talk. So when you want to model an accretion disk in the lab, a very good candidate for that is the Quad-Taylor device, okay, which is shown here. So it's basically you have two concentric cylinders that can be rotated independently. And in the space between your two cylinders, you're filling that with a conducting fluid, okay? There are several choices for the fluid you will use in this experiment. So in this case, the inner cylinder will represent the inner part of the accretion disk, and the outer cylinders, which is also rotating, will be representing the outer part of the disk. So as I was saying, you have different choices for the conducting fluid you will be using here. A very good choice is plasma, because it's a little bit closer to what's happening in a real disk. But unfortunately, it's very complicated to handle. It requires high temperature. It requires confinement of the plasma. It's very difficult to do some measurements in a hot plasma like that. So there is some brave people who are doing Quad-Taylor experiment with plasma in order to understand a lot of things about accretion disk. But another choice, much easier, and that's the one I've been following, is the one where you use a liquid metal. It's also a very good conducting fluids, but measurements and dealing of the liquid metal is much easier. And I'm illustrating that with the Princeton experiments, because it's been a very recent breakthrough for this MRI study. So in the Princeton experiment, the purpose of the experiment is to demonstrate that this MRI, this magnetorotational instability, occurs in a real fluids, in a real experiment. So you're rotating the cylinders, as I said. Of course, it's not a Keplerian rotation. Okay, if you remember your courses on quad profile, you know that this quad profile looks like that between two rotating cylinders. So it's different from a Keplerian rotation. It's not the square root law of Keplerian rotation. But it's okay because you can play with the rotation of the cylinders. You can set up the good rotation ratio so the profile is somehow close to the Keplerian rotation. What you really want to reproduce here is to get a centrifugally stable flow, to be below the Rayleigh instability of a rotating profile, okay? So you can do that. It's not so simple because then you have some end caps which are driving some recirculation. So I won't enter too much details here, but for the Princeton experiments, what they did is to rotate the end caps with different rings so they can minimize the recirculation. And as they are rotating in the centrifugally stable regime, the flow really stay stable. Okay, there is no fluctuations. Once you have that, you can just turn on the magnetic field. You can put some magnetic coils around the experiment. You turn on the magnetic field and you see if the MRI can destabilize the flow. Okay, I hope I'm clear here. That's a very basic idea. And I'm showing you that because very recently, this Princeton experiment, they reported the MRI for the first time in a laboratory experiment. So I'm illustrating that with their figure here. So what you're looking at is the evolution of angular momentum flux. Okay, you can access that in an experiment like that by measuring the radial and the azimuthal velocity fluctuations. So you have access to the flux of angular momentum. And they are measuring that as a function of the magnetic Reynolds number, which is basically the rotation of the cylinders. So just focus on the red curve. I will only discuss the red curve, which is the one which has the good value of the magnetic field. So by increasing the rotation, nothing happens, which shows you that, even at Rm 2.5 here, there is no fluctuation, no angular momentum flux, which makes sense because there is no MRI yet, but it's quite impressive because you see the kinetic Reynolds number for this value is already 10 to the power 6. So it's really a strongly vigorous flow, but because it's quasi-Keplerian, it remains stable. But then they reach this onset for the MRI, and then you can see that the angular momentum is starting to increase. The transport of angular momentum starts to increase. And that's a very good convincing proof of MRI. The onset matches some prediction, some theoretical prediction. It requires differential rotation, like the prediction of the MRI. The value of the magnetic field for which we observe the MRI is also in agreement with theoretical prediction. So it's been a very important step toward understanding the MRI because it shows that it's somehow a laboratory modeling of the initial state of an accretion disk. It shows that initially you can set up MRI and it generates a transport of angular momentum. Okay. Now, there is still some problem with this experiment when you try to extrapolate this experimental data to a real accretion disk. There is at least 3 problems with that, with this extrapolation. The first obvious one is the velocity profile. Okay, it's a very different velocity profile. It's not Keplerian. So it's quite hard to know what to do with these results when you want to extrapolate to a Keplerian velocity profile. That's the first point. The second point is that, as I said, it's a very good achievement. It's been extremely hard to reach the onset for the MRI in this laboratory experiment because it requires very high rotation of the cylinders. And for this reason, they can only go a little bit above the onset for the MRI. So as a consequence, you can see at this number here that the flux of the transport of angular momentum remains quite weak in this experiment. It's only at the onset of the MRI. So it has nothing to do with the fully developed angular momentum transport that we expect in a real disk. So it's very hard, again, to extrapolate these curves on several orders of magnitude to make a prediction for angular momentum transport in accretion disk. And the last point, which to me is probably the most important one, is that if you think about it, the angular momentum here is injected at the boundary of the system, okay? Because in this experiment, we are rotating the cylinders, and this is at the cylinders that we are injecting all this angular momentum that need to be transported, okay? And we know that the dynamics of angular momentum, how it is transported in a rotating system, is strongly influenced by how you inject that. In particular, when you inject the angular momentum at the boundary, it strongly drives the way it will diffuse in the system. I will come back to that, but it's very different. You know, a boundary-driven angular momentum is very different from what's happening in a real disk, in which the boundaries are not really involved in the injection of angular momentum. And as you will see, that will be an important, probably the most important point here. So what I will show you now is another experiment that we've been developing at ENS with the purpose of bypassing exactly these three problems that are encountered in Taylor-Couette experiments. Okay, so it's really complementary of what I showed you here. If the Princeton experiment is a very good demonstration of what's happening at the beginning of of an accretion disk when the MRI set up and generates the turbulence, the Kepler experiment is more trying to describe what's happening in the final stage. Okay, so that's our experiments. It's basically quite similar. It's two concentric cylinders again, which are filled with some liquid metal. The difference very clearly on this movie here is that the cylinders are not rotating anymore. So it's not a Couette-Taylor device. Okay. So how can we drive this rotation? What we're doing here is that we're using the fact that we have a conducting fluid, so we can inject some electrical current through the experiment. You can see some wires here on the movie, on the outer rim. And using this wire, we bring 3000 amps that are forced to go across the liquid metal and to be collected by the inner cylinder, which is just like one giant electrode. And so you have a radial current going through the liquid, all right? Then we place this disk between two magnetic coils, like in this drawing here, that generate a vertical magnetic film. So what you have is radial current cross vertical magnetic film, so it generates a Lorentz force in the azimuthal direction. And this is how we drive the flow here. Okay, so the Lorentz force here, so our magnetic Reynolds number is very small. It's smaller than 1 in this experiment. The MHD part of this experiment is only here to drive the flow. We're just driving the system like that. Sorry, so I'm gonna just turn on my mail here because the noise keep annoying me. Okay, am I still in? Am I still sharing my screen? Yes.
Yes, yeah, you are.
All right. So yeah, so that's how we drive the flow like that. So we are using liquid gallium. The disk is very thin. It's 1 centimeter in height, 40 centimeter in diameter. We need to inject a lot of current, 3000 amps. And we can do measurements of the velocity field in these experiments. I won't detail that too much. I can come back to that during the question if you want. To go very fast, you can see some probes in the experiment here. And these are some electrodes because we know from Ohm's law that when you have a conducting fluid crossing two electrodes like that, if you measure the voltage between the two electrodes, it's going to be proportional to the velocity field. So we have like local measurements of the velocity field. We can also do some ultrasonic Doppler measurements, which gives us access to the velocity field inside the experiment. And the last point here is that the real experiment is closed. I just removed the end caps here so you can see the liquid gallium flowing, but the real experiment has an end caps. It's closed. So that's our experiments. And this is typically what we get. We get what we were trying to complement compared to the Kepler experiment. We get Keplerian turbulence. You can see that on this first picture here. Each square is a measurement obtained from the experiment, and this is the angular rotation as a function of the radius. Okay, so clearly you can see that we have it's very well aligned with the dashed line here, which is the prediction for Keplerian rotation. Okay, so that's the first point. Our rotation rate in average is Keplerian. I say it in average because the flow is in fact strongly turbulent. strongly fluctuating. So you need to average during several minutes to get this velocity profile. The turbulence is illustrated by this second figure here. And so just focus on the yellow curve. I won't describe the other regimes, but if you choose carefully the good value for the current and the magnetic field, you get that. So these are the power spectral density, the power spectrum of the velocity fluctuations. And we get a K minus 5/3 signature, which shows you that the flow is strongly turbulent, which makes sense because we're rotating the liquid at several meters per second. So it's turbulent. So how can we, where is it coming from? Obviously, I don't have gravitation in these experiments. So how can we get Keplerian rotation? Again, roughly speaking, if you look at the force balance of the equations, you can basically see that because it's several meters per second, you can drop the viscosity in the first order force balance. And basically, the Lorentz force is replacing the gravitation in the force balance. So what we're doing here is that the Lorentz force, which is 1 over the radius, is in balance with the inertia of the fluid, which is like u squared divided by the height of the disk, which is h. Okay, and this force balance provides a Keplerian rotation. Okay, so to get this exact formula, we need to do the real calculation. Of course, this is just an order of magnitude, but which is in this paper here. But basically, the force balance between inertia and Lorentz force provides a Keplerian rotation, and this is a dashed line. Okay, so you see that there is a good agreement between this theory and the data. And of course, it's turbulence. So a very important point at this stage of the talk is to say it again, it's not an MRI experiment. The turbulence we have here is not driven at all by MRI. Okay, we don't want that. If you want to know exactly where it's coming from, it's because we have end caps. So just like so you remember in the Princeton experiments, I told you that they have to take care of the end caps so they reduce the circulation, for instance. So they can keep a flow which is laminar when they set up the MRI. We're doing exactly the opposite here. We have a very small disk, so the circulation is very important, and it generates a lot of fluctuation. And because we are increasing way above the destabilization of this circulation, at the end, at several meters per second, we get a fully turbulent flow due to these fluctuations, due to the end caps. And that's exactly what we want. Okay, we want to be far enough from any onset. We want to be in a stage of fully developed turbulence, but keeping a Keplerian rotation rate for the time average velocity field. And that's what we get here. Okay, so that's why I'm saying that in this regard, this experiment is describing the final stage of an accretion disk. Okay, so that's so far the description of the experiment. So now with this experiment, we can try to study angular momentum transport. So you all know that in a real disk, we know that the velocity is a Keplerian rotation plus some fluctuation. And we know that the accretion rate is related to the flux of angular momentum. So I'm writing the flux, the radial flux of angular momentum here. So there is one term which is related to the viscosity. Okay, nu is the viscosity. So this term is simply the viscous friction, the viscous transport of angular momentum. And in general, in a real disk, it's very small. And there is this part here, which involves the correlation between a radial and azimuthal velocity field. And this part is going to be very important when the flow is fully turbulent. Okay, so that's your flux of angular momentum. And that's related to accretion ultimately. In the laboratory experiments, okay, we don't have accretion. I don't have any black hole in the experiments, but we can measure this flux of angular momentum. When the flow is turbulent, there is a redistribution of angular momentum. So there is an outward flux of angular momentum. And you can see that we can measure that because we can measure the radial velocity, we can measure the azimuthal velocity, we can measure the gradient of the velocity in the experiment, so we have access to that. So to get a scaling law, since I want a scaling law, we need a dimensionless measure of this flux. So what we are doing here is to introduce a Nusselt number where we are normalizing this flux by the value of the flux where the flow is laminar. Okay, you can see that this is a laminar expression for the flux of angular momentum, just taking this viscous part of the flux. It involves the viscosity. Okay, so basically the Nusselt number is 1 when our flow is laminar, because this is corresponding here, so it's 1. And as we increase the level of turbulence, Nusselt number will become larger and larger than 1. Okay, so it's a measure of the efficiency of the turbulence to transport angular momentum in the experiments. And we basically want to understand a scaling law, so how this Nusselt number depends on the level of turbulence, which is here measured by the Reynolds number. So that's the basic question we're asking with these laboratory experiments. And that's what we get. So we are measuring the Nusselt number in the experiment. This is here, as a function of the Reynolds number. In this experiment, we are increasing the Reynolds number by increasing the current. And we do that for different values of the magnetic field, which correspond to the different colors here. Okay, so you fix the value of the magnetic field, you increase the current, then you do that for several values of the magnetic field. That's really the take-home message of our paper here. Okay, that's the main results of this laboratory study. So what can we say? First, it's quite obvious that we have a clear scaling law. Okay, you can see that the Nusselt number is really seems to evolve linearly with the Reynolds number. Okay, that's the first obvious observation. The second observation is that this scaling, this linearity between Nusselt and Reynolds, seems to be quite independent of the value of the magnetic field. It's always the same slope. It's important. And if the magnetic field is not too strong, which means that if you ignore the green data, which are really obtained for a very large magnetic field, all the other values of the magnetic field are collapsing together. You have one single prediction for the transport of angular momentum independently of the value of the magnetic field. Okay, it only depends on the Reynolds number. So why are we happy with these results? It's because, in fact, this prediction was predicted a very long time ago by Krecknan in the 60s. So I won't show you the calculation by Krecknan. It's like 10 pages. And the calculation is quite complicated. But I'm not showing you that because it can be recovered very simply. Because it's based on very universal assumptions on turbulent transport. When you follow the paper by Krecknan, you can see that basically what it requires is first an asymptotically high Reynolds number. You need to be far away from any threshold which is driving the turbulence. You need to be in a well-developed turbulence. You need your boundary layer to be turbulent. You need the bulk flow to be turbulent, and so on. The second important hypothesis is that it must be independent of the boundary effects. Okay, the boundary must not be involved in the driving of the angular momentum. And finally, a last important point is that you need the molecular diffusion coefficient to be not important. Okay, you need the flow to be so turbulent that it doesn't care about molecular diffusion anymore. There is no molecular transport of angular momentum. And basically, if you have these three assumptions, you can get this Nusselt equal Reynolds number scaling. Okay, it's very simple. You can see that by dimensional analysis actually. So we are looking for this scaling law, right? We're looking for the Nusselt number depending on the Reynolds number to some power beta that we don't know. So I rearrange these terms. So this is the Nusselt, J laminar, times Reynolds to the power beta. If these three assumptions are met, it basically means that you have large Reynolds number, you have no viscous layer on the boundaries, there is no non-molecular transport. So it means that the flux J here must become at some point independent of the molecular viscosity. Okay? And since you have nu here and nu there, you need beta to be equal to 1 to get that. And that's how you get this Nusselt Rayleigh scaling. Okay? If you look carefully at the Krecknan paper, it has been done in a way different than angular momentum transport. That's been done for heat transport, but this is exactly the same argument. you will find that. And if you want the prefactor here, you of course need to describe the stratification, the average stratification of the angular momentum. And in our case, it means that you need to take into account the Keplerian rotation rates of the system. And if you have that, you have the prediction for the scaling law. Okay, so now you understand that, we can come back to this picture and you see, so this is a prediction, the Craig-Nance prediction. So why is it interesting? First, it is interesting because it shows that indeed, the prediction by Craig-Nance can be observed in a real experiment. Okay, there is some possible ultimate transport. So people are calling that ultimate transport of angular momentum. If you look in the literature, you will see that previous experiments using quad-Taylor device find a different exponent. It's not 1, it's 0.76. But now I think, I made a lot of efforts in this talk, so this exponent makes sense. In quad-Taylor device, we are injecting the angular momentum at the boundary, right? So when you do that, you have a viscous layer where you're rotating your boundaries. And so your transport of angular momentum relies on this viscous layer. So you can never forget about viscosity. You can never do this trick of making J independent of the viscosity because you always have to deal with the viscous layer. And that's why when you use a quad-Taylor device, you get these exponents. In our case, we did everything. That's why we did this experiment. We are injecting the angular momentum in volume with the Lorentz force. We don't have boundary injection of angular momentum, and we can drive the system far away from the onset for the turbulence. So we have fully developed turbulence, and all the conditions by Craig-Nance are met, and that's finally why we get this ultimate regime. Okay, so I hope the difference between the two approaches are quite clear. And it brings me to what is probably of more interest for people following this talk, is the comparison with observations. So if you follow carefully what I said here, I haven't used very complicated arguments. What I'm saying here is that this scaling, this purple scaling, is basically constrained by dimensional analysis, turbulent flow, and Keplerian rotation rates. It doesn't care about the details. It doesn't care about the aspect ratio or the exact fluid which is used here or the fact that we're driving a current and these kind of things. It's an asymptotic result. And there is some hope that we can use the data from the experiments and say something about the real disk because of this universality. So it's the part of my talk where clearly it's dealing with astrophysics, and I'm not an astrophysicist, so maybe I will. I have to rely on someone else's results very clearly. So here I'm following what has been done by these people here, Hersan and Dubrul, I think, a long time ago, where they're relating, of course, the angular momentum flux to the accretion rate of a real disk. Okay, it can be related to the parameter of the disk. M dot is some parameter about the typical specificity of an accretion disk. And so if you rearrange this formula here, you can construct a dimensionless number, which is called the dimensionless drag coefficient. And of course, it's going to be related to the accretion rate of the disk. It's an alternative to what people here know more, like the turbulent viscosity of the alpha disk parameter. Okay, it's a different measure of the turbulent viscosity or the accretion rates, which is written like that. And in this paper, they are plotting this gamma parameter. This is gamma as a function of the Reynolds number. And each point here is a different accretion disk. So these are observations to give a good idea of this parameter. The reason why I'm focusing on this parameter and not alpha or nu t is because we can also compute very conveniently this parameter in the experiments. Okay, because we can compute everything which is involved in this gamma parameter. If you follow the talk carefully, you will see that, in fact, gamma is simply Nusselt divided by Reynolds number. And this is how it looks in our data. This is gamma. This is the Reynolds number. Again, forget about the large-scale green magnetic field, which is a different regime. But you can convince yourself that as we increase the Reynolds number, it seems that the data are converging to a given value here, which is the dashed red line here. Which makes sense because, as I said, the ultimate regime means that Nusselt is scaling linearly with the Reynolds number. So this ratio, this gamma parameter, when we are on the ultimate regime, is simply a constant with this value in our experimental data. And you see, if you plot this data, this experimental prediction on the observation curve, it comes here. Okay. So we are very happy with that because you can't play the same, you can try to play the same game with Taylor-Quate devices, but it's much more complicated because this ratio, this gamma parameter, is not constant. Because with Quate-Taylor device, the system is not on an ultimate regime. Nusselt is not linear with Reynolds number. So you need to do some complicated extrapolation. Here we don't have to do that. We have a simple answer. And you can see that the agreement is not so bad. Okay? So that's really like the conclusion of the first part of my talk. What can we say about this conclusion? I guess what we're saying here is that turbulence, in the sense turbulent transport on the ultimate regime, is a good explanation, is a good first order explanation for these accretion rates. I know that there is some debate in the community on whether turbulence could explain the transport of accretion disk. Here we are bringing some constraint. Okay, what we get from the experiment are only based on very universal behavior, like, as I said, the ultimate regime in far away from in the well-developed turbulent regime, and it's matching some of the data. Not all of them. Clearly, there is second-order differences with this simple explanation that explain why some disks are very far from that. But at least it matches quite well. A second constraint here is that, you see, what I've been telling here is really the transport achieved by the Reynolds stress, by the hydrodynamical turbulence. If you have MRI, for example, if the turbulence will be driven by MRI, you will have a transport due to the Maxwell stress. So what we're saying here is that this is a minimal bound. Any disk which is way above this minimal bound might be due to Maxwell stress. So it will be too interesting. I have no idea how to do that from the observation, but it will be interesting to see, for example, this data very far from this purely hydrodynamical prediction from the experiment, or the one which are involving Maxwell stress, for example. Okay. Okay, so that's for the transports. I'm guessing that I have maybe 10 minutes left. Is that correct?
Yes, something like that.
All right. So just for the last 10 minutes, I would like to say a few things about this cycle. Okay. Okay, so we can convince ourselves that turbulence can explain accretion rates, but we need to understand where the turbulence is coming from. Okay, and I described to you this very nice peeling cycle. It has not been addressed so far by experiments. We need new laboratory ideas to get that. It's very complicated to get. But beyond laboratory experiments, we also need to understand clearly, to describe, to have a dynamical model, a low-dimensional model, which help us to understand what this cycle is capable of producing as a prediction for the turbulence. And as you will see, this question goes a little bit beyond accretion disk. So my starting point to discuss that is a different simulation that I've been doing with Ludovic Petit-Demange and Florence Marcotte. So it's a different object. It's what's happening in the interior of radiative stars. So it seems different, but you will see that it's actually the same question. So to go very fast, I won't enter into any details comparing about that, but we know that in stably stratified radiative interiors, there is no convection, there is no source of turbulence. But we know that there is a massive transport of angular momentum because we know that the core of the radiative stars is basically in solid body rotation with the outer part. So there is a spinning down of the inner part of the star, which is due to a massive transport of angular momentum. And that's basically the same question then for accretion disk, because We could invoke turbulence, but in a stably stratified region, a non-convective region, we don't know exactly where the turbulence is coming from. And so with my colleagues, we've been doing some simulation of that. And we found a scenario, which is again something that has been predicted a long time ago, which is called the Taylor-Sprout dynamo. Again, I won't detail too much, just focus on this time series of the energy. What we observe here, and which is coherent with this prediction, is that you start your simulation, you have a laminar stellar interiors. But the magnetic field is increasing. It's increasing because of the differential rotation, for example, or because of a laminar dynamo. Most of the time, it saturates at a low value and the flow becomes laminar and there is no transports and you can't explain the spin down of radiative stars. But sometimes, if the magnetic field becomes strong enough, there is a secondary bifurcation where suddenly the flow becomes turbulent and the magnetic toroidal field, large-scale field, becomes very large. Okay, so very rapidly you have a generation of a turbulent field and a large-scale magnetic field. And that's how people are describing this cycle. You start with your large-scale toroidal field, it becomes unstable, it's known as a Taylor instability. It's not the MRI, it's a different instability of a toroidal field. It creates some turbulence, and then the turbulence is very efficient to goes back, generate the initial toroidal field, and you have this amplification loop. This is exactly what explains this amplification in the data here. Okay. The reason I'm showing you this simulation is that, as you can see, it's completely similar to what people are considering in accretion disk. We have a large-scale field. It generates turbulence through some instability. In accretion disk, it could be MRI. In radiative interior, it could be the Taylor instability. And you could put some other magnetic instability, magnetic buoyancy instability, for instance, these kind of things. And then the turbulence will go back to that. And we've been very interesting with that with Florentin Daniel because we realized that if we have so many systems that are showing a very similar behavior, maybe we can build a very simple model capturing this behavior. And so that's what we try to do that. So to do that, we have to use bifurcation theory. So the first step here is to identify what are the typical velocity and magnetic modes that are involved in this scenario. If you followed what I said for MRI or for these radiative stars, we obviously need a large-scale magnetic field, B. Let's call it B. Through some instability, we know that it's going to be unstable and create some magnetic perturbation P, right? And then some turbulence that I will represent by a velocity mode V, which is a small-scale velocity mode. So you need an equation for these three modes. If you want to do that carefully, you need to do a perturbative calculation of the MHD equation from the initial equation. And it's going to be very complicated. And I don't know how to do that. Maybe some people know, but it's very complicated. But you don't have to do that because when you identify the relevant mode in your system and when you know the symmetry of the equation you're trying to solve, most of the term can be guessed by symmetry arguments. Okay, so what you do in general is do a Taylor expansion of these amplitudes, okay? And there is a bunch of terms. You can do B, B squared, BQ, B4, and so on. But thanks to the symmetry, for example, let me just illustrate that with one. So there is no B square terms here. I should have this term in the classical Taylor expansion, but I'm not because I know that MHD equations are invariant with the B minus B symmetry. So I don't have to put this term. And I can play this game for the three equations. And at the end, if you stay at third order at maximum for this system and that you just use these three amplitudes and the symmetry of the equation, that's the minimal model which is compatible with this cycle here. So very simply, we are constructing here a very general model. It can't be something else because it's constrained by the symmetry of the modes which are involved in this system. And this is very easy to simulate. You can simulate that with MATLAB or Python. And you can see that, so so I don't have to describe that, but you could identify, for example, this blue term or the dynamo term. The green term is the MRI. The blue term is the saturation of the Lorentz force. All of this is constrained by the symmetry. What is not constrained is the value of the parameters, which are completely free. You have to fit this model to the DNS, for example, to get something. But I'm telling you that because I think it's a very powerful approach, which is not followed too much by the astrophysical community, and it really provides very interesting answers. For example, you can constrain the parameter by fitting your DNS with the model. Once you have done that, you have the value which are fixed for this parameter. And then you can study the prediction for this model. That's so, for example, we obtained that this model is predicting that the occurrence of turbulence through this cycle has to be subcritical. Okay, that's the main outcome from this data. And that's my second, conclusion for this talk. If turbulence in accretion disk is generated by some cycle like that, the symmetry of the system are mostly, I think, imposing that the bifurcation to the turbulent should be theoretical, and we can compute, on what is the size of the hysteresis, in which region can we still get turbulent flow when the linear profile is stable. These kind of things. We can predict the typical seed for the amplitude of the magnetic field, which is necessary to trigger these magnetic loop cycles. And I believe it will be interesting for understanding accretion disk. Okay. Okay, so that's my conclusion. So the first part is really to obtain a scaling law, which I believe provides some prediction quite universal for the transport of angular momentum by turbulence. At least by turbulence, not by something else. You could imagine other scenario for transporting angular momentum, but if you want to involve turbulence, it should be constrained more or less by this prediction. And the second part is just like trying to motivate people to use this approach to make some prediction on the dynamics, on the transition to turbulence in this astrophysical system that I think might be very helpful. And I will stop here. Thank you.